Hi, AP Physics and regular physics student. Mr. Dranko here with your next video and assignment in our chapter on DC circuits. We did some series circuits last time. This time we're going to do parallel circuits. So let me get right to the slides. So parallel circuits have the components arranged such that there are multiple paths for the current to flow. And you'll see some examples of that shortly. The resistors, if they're in parallel, the equivalent resistance is not the sum of the resistor values, but it follows this equation. And so that's very different. The current that flows out of the battery, the load current, is the sum of all the currents in each resistor. And I'll show you why that is. And parallel circuits do not require all the components to be working for the circuit to work. And that is seen in our lights on our Christmas tree. When one bulb burns out, the whole tree doesn't go down because of that. And so there's some parallel circuitry there. Let's take a look at this example. So we have a 9-volt battery, and we have three 30-ohm resistors connected in parallel. So this is 9 volts, and each one of these are 30 ohms, 30 ohms, and 30 ohms. So you can see how this circuit is configured compared to the series. The current can flow this way, or it can flow this way, or that way. And so there's multiple paths, and that is sort of the easiest example of a parallel circuit. And so we have to find, in this example, the equivalent resistance. So 1 over R equivalent equals 1 over 30 plus 1 over 30 plus 1 over 30. And so 1 over R equivalent equals 3 over 30. And so R equivalent is equal to 10 ohms. And you can see that the resistance, the equivalent resistance, will always be lower than any of the resistor values. And so if you calculate equivalent resistance and you don't see that relationship holding, then you may have made a mistake in your math. Okay, so what the battery really sees is this. This is what the battery sees. It sees that. And so we can find the current in each resistor and the current drawn by the circuit load. The current that flows out of the battery is just obtained by V equals IR. In this simple circuit, it's 9 volts. The current is what we're looking for, and the resistance is 10. And so I is equal to 0.9 amps. So 0.9 amps flows out of the battery. Now, to find the current in each of these, we're going to use, again, V equals IR. Let me erase this up here now. The voltage across each of these resistors is 9 volts. You can see there's nothing that gets in the way of my fingers between the battery and these junctions. And so we can use V equals IR. The voltage is 9 volts across that resistor. We're finding the current, and the resistor is 30. And so the current comes out to be 9 over 30, which is 3 over 10, so 0.3 amps. So 0.3 amps flows here. And if I do this calculation over and over again, I get 0.3 amps here and 0.3 amps here. And you can see that the currents sum due to the conservation of charge. 0.9 is equal to 0.3 plus 0.3 plus 0.3. At this junction, 0.9 amps comes in and 0.9 amps flows out. So let's stop here and give you a problem to try. I hope everybody is doing fine. This is the last video before Easter, so hopefully you'll have a great Easter, and if you don't celebrate that, a good and safe weekend. Bye-bye.